Hello class, my name is John Davis. This is my presentation for CSC 338, Algorithm Design. We're taking a look at Karatsuba's algorithm, a divide and conquer implementation for integer multiplication. So let's take a look at a problem mankind has had to face many times before. Just imagine, the year is 1859 and you're a settler of the Pacific Northwest. You farm wheat and each bushel of wheat sells for 25 gold each. If you sell 8 wheat, then what would the total sale be? Let's identify what we're doing here. We have a bunch of wheat that can be represented as the quantity 8. Each wheat will sell for 25 gold, or in other words, for each quantity of wheat sold, we profit 25 gold. Pretty quickly, you'd probably be able to figure out that the total sale was worth 200 gold. Good job. Word goes around town and business starts to pick up. Suddenly, you're getting more orders than you can even account for. The next order comes quickly and you're ecstatic. 31 bushels of wheat. The customer asks you what you owe, and no sweat. You've done this kind of problem before. As you start to do the math in your head, another order comes in, this time even bigger than the last one. 1,421 bushels of wheat. How much money should the customers have to pay? Pretty quickly, you can see how this relatively easy problem can start to scale up. Now imagine if we were dealing with millions of bits or numbers that are hundreds of thousands of digits long. We'd have to develop some sort of a system to help us multiply the numbers. In ancient times, the Babylonians relied on a base 60 number system ranging from 1 through 59. For 1 through 9, the same symbols would be used to represent the amount. If you look at 2, it is 2 ones stacked side by side, 3 is 3 ones, 4 is 4 ones, and so on. This pattern repeats for multiples of 10s as well, denoted by bottom row. This number system is primarily used for counting, and there is no way to denote 0. Some of the first records of a base 10 or decimal number system date back to ancient China. Pictured here is the multiplication table from 305 BC. For many calculations, people had to rely on things like multiplication tables instead of something like a calculator or even a well-established way to multiply two numbers or even really do math. One of the first methods established for multiplying two integers is a method known today as Russian peasant multiplication. Let's say we have two integers, 17 and 21. We start this method by splitting the two integers to the left hand and right hand sides. Next, we start to half the left hand side and double the right hand side. On the left hand side, we divide by 2 and throw out the remainder. In our example, 17 becomes 8. The right hand side is doubled and step 2 is repeated until 1 is on the left hand side. For all odd numbers on the left hand side, we'll add the right hand side. In this case, the only odd left hand side numbers are 17 and 1. Therefore, we add 21 and 336 to get a correct product of 357. This method does not require any memorization of any products less than 10, and for an integer with size n, the two integers multiplied together will take at best n squared number of computations to compute. In our example, 17 and 21 both have a size of 2, meaning there are 2 digits. As underlined, it takes 4 computations, or 2 squared times, to get our product. Therefore, the time complexity of multiplication using this algorithm would be big O n squared. The method you're probably most familiar with is a method of multiplication called long-form multiplication, or more commonly known as grade school multiplication algorithm. Let's say we have two integers, x and y. We start by stacking the two integers. The top value is known as the multiplicand, and the bottom value is known as the multiplier. We first start by multiplying the top value by the rightmost digit in the bottom value. In our example, we are multiplying 17 with the 1 in the bottom. When the last value has been multiplied in the top, we shift to the next value in the multiplier, which in this case is the tens value, which happened to be 2. Simultaneously, a 0 is added to the p over 10 position, where p represents the place value. After padding with zeros, the new multiplier is multiplied with the top number, and this step repeats for all values in our multiplier. Once all values have been iterated through in the bottom number, we sum together the products from steps 1 and 2. This method is relatively easy to learn and is the method most commonly taught to children in school. Unlike the Russian peasant method, this method requires memorization of times tables less than 10. When observing our example, you can see that n is equal to the size 2. For each digit in n, we do n number of calculations. For example, 1 gets multiplied twice, 1 for each digit in the multiplier. The same thing happens to 2 as well. Therefore, the lowest number of computations required to get our products is no less than n squared steps. Therefore, big O is O(n) squared. By now, you might have started to pick up on a pattern with our two algorithms. So far, the lowest number of steps to take when multiplying two integers of size n is no less than n squared steps. For a while, it was believed there is no faster way to do multiplication. In 1960, Andrei Kolmogorov, an at the time Soviet mathematician, called this problem the O(n) squared conjecture. He himself could not find a faster way of multiplication, but he also knew as a mathematician that more possibilities existed. On Moscow State University, Kolmogorov hosted a cybernetics seminar specifically to tackle what was called at the time problems in the complexity of computation. This event is largely responsible for kickstarting a new branch of mathematics known as algorithm efficiency. What he did was invite other mathematicians as well as students majoring in math to try to dispute this O(n) squared conjecture. One of the students present was 23-year-old Anatoly Karatsuba. He would go on to find an algorithm that had a runtime complexity of O(n) to the 1.58. Anatoly Karatsuba lived from 1937 to 2008. He was born in Moscow, Russia, and at this time he was attending the university as a junior. He found out that his algorithm was published only after Kolmogorov published the algorithm, thankfully under the name Karatsuba. This algorithm ended up being the earliest known divide and conquer implementation for multiplying numbers. To better understand Karatsuba's algorithm, let's review the basics of a divide and conquer algorithm. In computer science, a divide and conquer algorithm refers to an algorithm that takes the original problem and divides into smaller, more manageable subproblems in order to find a more optimal solution. The algorithm is ran recursively on the smaller subproblems and then joined together to form the answer of the original problem. Let's take a look at the figure on the right-hand side. At the top, there is a list of unsorted numbers ranging from 38 to 10. Additionally, the list has a size of 7, and let's call the size of the list n. After each iteration, we divide n by 2, and we repeat this process until we reach a base case, in this case when n is equal to 1. The new list of numbers are then sorted, first in pairs, and then 4s and 3s, and the algorithm is recursively called again, and then the results are interread one last time. The final list of numbers represent a new list of numbers, sorted using a divide and conquer algorithm. Before we take a look at the math, let's see proof of this algorithm in action. Let's say we have two positive integers, x and y. Our first step is to split the integers into high and low parts. For example, let's say x is equal to 17 and y is equal to 21. We're going to denote a and c for the first high order digits and b and d for the low order. Additionally, the size of both digits is 2, therefore n equal to 2. Our first step is to take the product of digits a and c. Next, we take the products of digits b and d. Afterwards, we'll add and then multiply a and b by c plus d. Once we get these values, we'll take our product from step 3 and subtract steps 2 and 1. Now we take our value from step 1 and pad it with n zeros. Next, we'll take the value from step 2 and pad it with no zeros. Below that, we'll plug in our value from step 4 and pad with n over 2 zeros. Our last step is summing together the three values. With n being 2, we are doing a total of 3 recursive calls. The resulting runtime is O(n) to the 1.58. Like any other divide and conquer algorithm, the general idea is to split the problem, multiply the halves recursively, and then recombine to get our final product. Now that we know how Karatsuba's algorithm works, let's see how he came up with it. So let's try to come up with a divide and conquer algorithm of our own. Let's say we have two integers, x and y. For simplicity's sake, let's also work in binary. An important distinction with any base number system is that raising a number to its base times some number will shift that number according to the size of the exponent. For example, 4 times 10 squared will shift 4 to the right twice. In a binary number system, an integer multiplied by base 2 will shift that number by the exponent n number of times. This will become more obvious in just a bit. In our divide and conquer algorithm, let's divide the size of our problem. We can do this by dividing the bits into high and low order parts, denoted here by a, b, c, and d, as well as x is equal to 2 to the n over 2, a plus b, and y is equal to 2 to the n over 2, c plus d. So far, nothing has changed, and as mentioned earlier, we are simply shifting the high order parts by 2 to the n over 2 spots. Let's rewrite our equation to x times y is equal to the products of the aforementioned sums. Next, we'll distribute our right-hand side equation to get our intermediate equation. Lastly, we'll combine like terms to come up with a final divide and conquer equation. Although we come up with the divide and conquer approach, we're still left with the final calculation that requires at least 4 products, or at best, n squared number of computations when multiplying two integers of the size n. This is where Karatsuba used clever manipulation of basic algebra to come up with an equation that not only used one less recursion, but was also able to reduce the total number of sums as well. Note that the products of sums a plus b and c plus d can be distributed to be rewritten as ac plus ad plus bc plus bd. Let's review our divide and conquer algorithm from before. At this point, you may be able to notice that we have these 4 groups of numbers that represent the products that get calculated. Karatsuba's trick is to group together these numbers in such a way that the original calculations performed, a times c and b times d, can be reused in the equation, here by subtracting ac and bd from the part inside the brackets. We can rewrite our divide and conquer algorithm to now become Karatsuba's algorithm, again by using nothing more than simple algebra. Here is the pseudocode for the algorithm. Our function has one input of 2 integers, x and y. If the size of the bits is less than 2, the numbers are just multiplied straight across. Otherwise, we split our integers into high and low order parts. Then, we recursively run our algorithm at each high and low order part, which if you see up here, just another way of redoing our steps from earlier. The function returns the algorithm at their subtracted steps 1 and 2 from 3. So using basic algebra, Karatsuba was able to disprove the O(n) squared conjecture, and he did this in less than 2 weeks. Lastly, here is a pseudocode written in Java and its corresponding output. Thank you.